In this example, I want to go through how to derive an analytical expression for representative monotonic probability transformation. Specifically, we say, given an input variable x who has a uniform probability density limited over the range from minus pi to pi, as well as a representative transformation y equals arctangent of x, which is a monotonic transformation, we seek to find the analytical expression for y's probability density. With this expression, we can derive all the moments of y, such as the mean value of y, say this leads to that, the variance of y, etc. Basically, once we have this expression, we basically have these fundamental statistical characterization of y. And just to review, this is the mapping of arctangent of x. Just to demonstrate, it is a monotonic function. There is, over the interval of x from minus pi to pi, there is exactly one y to each x. So that's what we mean when we say monotonic. So using our result we derived last time, that basically came from the equivalence of the probability densities, which I'll rewrite here. We recall that this expression led to the following. For y equals some mapping f of x, and x equals the inverse mapping of y, we say a piece of y equals a piece of x of, instead of term x, we want to say the inverse value of y times absolute value dx dy. This fundamental expression is what we will use to take our known p of x, our known mapping, which is also encoded here, and with these derive our desired y density. So in our case, we have y equals arctangent of x. That's our y equals f of x. We also have x equals tangent of y, and that's our inverse mapping. We have let's go for this guy, dx dy equals, and I'm going to show you a quick trick here. So here I want to use the MATLAB symbolic toolbox to derive what the this particular derivative term is here. So in MATLAB, I start by defining a symbolic variable x, actually y. Then I'll say x equals tangent of y. So the question is, if I can't remember my derivative terms, I know the derivative of tangent is secant squared, but I just want to use MATLAB to show how the symbolic toolbox can be used as a derivative lookup effectively. So we say diff of x, I think you can say with respect to y, and it will give you an expression for x. So you're probably wondering, okay, you said this was secant squared, well that doesn't look like secant squared. So actually tangent squared y plus 1, remember tangent sine over cosine, so it's basically sine squared y over cosine squared y, plus 1 is cosine squared y over cosine squared y. And so you'll recall that's sine squared y plus cosine squared y all over cosine squared y. You'll recall from your trig identities this term is actually 1, so that's equal to 1 over cosine squared y or secant squared y. Anyway, I just wanted to kind of briefly go through how you can use the symbolic toolbox to do your derivative lookups instead of Googling it, which is also an option. So going back here, we'll say this term is equal to 1 over cosine squared y. The next thing we'll need to plug into this equation is how to map this probability density piece of x And basically what we have here is, let's write out the official description of the uniform density. We have P of x equals, it's 1 over basically this endpoint minus this endpoint for x values within there and 0 otherwise. So it's basically 1 over pi minus negative pi, or as we can simplify in place, 1 over 2 pi for x between minus pi and pi. Otherwise it's 0. So what we want to do is take this, use this inverse mapping, and basically get an analytical expression for this term. I'm moving my terms around a little bit here, but basically we want to get this term in terms of this term. Well, the first thing to look for is all presence of x need to be changed to tangent of y. Well, for this particular density, there is no x term here, there is no x term here. All you really need to do in terms of transferring x to y is to address this particular limits. Specifically, when we say x has, this minus pi and this plus pi, to what y do those correspond? So that's basically what we're going to do, and we find that at x equals minus pi, we find y to equal, pulling up MATLAB, we say what's the arctangent of minus pi, and let's say minus 1.26, and I believe it's it'll just be the sign change for the other term. That's correct. So we'll return to our expression here and say, let's say at x equals plus or minus pi, y equals plus or minus 1.26. So we can then say piece of x of f inverse y equals 1 over 2 pi times, or I should say for y, an element of minus 1.26 to 1.26, and it's 0 otherwise. So at this point we have this, we have this, so we have everything we need to reconstruct our analytical expression. So doing so, plugging in the terms of this equation, rearrange things a bit again, but we'll say a piece of y is therefore 1 over 2 pi cosine squared y for y on minus 1.26 to 1.26 and 0 otherwise. So this is the fundamental statistical characterization of y given this particular mapping and this particular prescription for x's statistical properties. So this is our answer, and now I'm going to show a way to compare this answer to our numerical estimate of y's probability density. So first of all, we want to determine how many, we're basically going to create a numerical approximation to the density, and to do that we need to say how many samples we want. So let's just go with 1,000,000 samples for now, and let's generate some x values that follow our prescribed x density as shown here. So we say we want x to be uniform. For the uniform density, the inputs follow next are minus pi and pi, the extents. And now we want to say how big is x, what are the dimensions of x. So we'll say one row by n sample columns. So that gets us our x, and in case you want to see what x looks like, we can go ahead and just do a histogram of x, and I'll just do this, and that kind of agrees with what we expect, a uniform between minus pi and pi. So anyway, going on, we want to get some sample values for y, and so we just push these values of x through our mapping function, arctangent, as seen here. And now we want to get a histogram-based approximation to the density of y. So how many bins do we have? My convention is to do the square root of the length of the vector, or the number of samples, I should say. And so we can go ahead and see what, let's see actually, histogram in terms of our sample y's, and use this many bins. So this will give us a kind of a quick look at what our histogram of y is. So what we want to do now is actually extract, let me plot that again, we want to extract what these values are here, and we want to normalize them such that, you recall that the integral of a density is 1 by the normalization requirement. So that's basically what we want to enforce here. So we're going to pull out the y locations in the histogram into this variable, and then the x locations, or I should say the horizontal locations, into this variable when we call histogram. This will not produce a plot, but we will have all the values there. Now we want to normalize our density. First of all, we need what our dy value is, so that's the y bins 2 minus y bins 1. And finally, we enforce the normalization requirement. We take our existing value and we divide it by the sum of piece of y num times dy. Doing so enforces normalization. Specifically now, if we say some piece of y num times dy, we get a value that is unity. Prior to that, we got some unnormalized term. So now we can plot this numerical density, and this is what we get. So this is our numerical based, or I should say sampling based density. We want to now plot our analytical result on top of this and see if they agree. It's kind of a way to check your answer. So since I'm going to be plotting on top of it, I'll just say hold on. That means I can plot on top of it. And let me go ahead and just set my axis font to something a little more hopefully legible for you. Maybe too big. Okay, so now we're going to plot, or I should say set up our derived analytical result. Let's make it an anonymous function for any value of y, and we'll say we're just basically going to copy and paste this guy. 1 divided by 2 divided by pi divided by cosine of y squared. Now before I go further, we're going to be giving this anonymous function a vector of y's, and so we need to do the vectorized exponentiation here. Also need to do a vectorized division here. So we have that, and let's just, as a quick check, make sure that our analytical result is in fact normalized. We'll feed it the value of y bins, and we'll say dy, and this should come out to 1 if we did things correctly, and it does, so that's encouraging. So now we want to basically plot our analytical result on top of the numerical. So we'll say plot x values of y bins, and for y values piece of y of y-bands. To differentiate, let's make it red in color. Let's make it a bigger line width as well. And hopefully it plots on top of the numerical result. And that's what we see here. It does. The red plots on top of the blue. So finally I'm going to just touch this up a bit. We'll say, we'll set the legend from numerical sampling. 6 terms. That describes our numerical, our blue curve. For our analytical result, we'll say from analytical expression. Alright, there's just a legend. And let's go ahead and give it a X label, values of Y. Let's just wrap up work. Y label, prob density, piece of Y. That'll do it. And finally, we'll give it a title, verification of analytical result by comparison to numerical. Alright, and in this plot we basically checked our answer against a numerical simulation. So that's an example of how to derive an analytical expression of probability density.